morning.
Good morning, sir.
I'm very happy to welcome Professor Mohan Krishnan. I think he's from University of Detroit University. He's a professor emeritus and has been there for more than 30 years. Yeah, 30 years? Too long. Yeah. And I'm sure that all of you are lucky to have him here. And he will be taking class on mobile robots and almost around 30 to 40 hours of lecture will be there. As I inform you, we will have two evaluations, okay, and I will be using that evaluation for your quiz one use. Okay, and the method of evaluation we think will be explained. Yeah. And I request all of you to make use of this wonderful opportunity, and I'm sure that it will be helpful for you in all your future studies, future careers. And I understand none of you are attending that value-added course. It's okay, but the same way we are going to record this value-added course also. Those who are interested to listen, we will be doing that, and we will be making two teams group. Already made. Some of them have been added. Yeah. Some I still have that. So if you want to interact with sir, you can interact. And the free times, sir will be sitting in the TIFAC discussion group. So if you want to discuss with him, you can do as well. And for your benefit, at the end of this course, those who complete this evaluation 1 and evaluation 2 will be giving a certificate stating that you have undergone mobile robots and ROS certificate course conducted by Dr. Mohan Krishnan, in addition to the regular classes. Okay. So today is the introduction class. Before Professor Mohan starts, I request Dr. Abraham to give an introduction about Dr. Mohan Krishnan. And in future, I think all the labs and everything will be done by Professor Abraham and the guidance of Professor Mohan. Thank you very much. I request all of you to take it. The timetable and everything will be given to you. Yeah. So, good morning, everybody. So, thank you, sir, for the introduction. So, I'd like to formally welcome Dr. Mohan Krishnan. Dr. Mohan Krishnan, he's a professor emeritus at the Electrical and Computer Science Department at University of Detroit University, Michigan. He has been, he did his bachelor's from IT Madras and then his MTech again from IIT Kanpur, and then did his PhD from the University of Windsor, Ontario, Canada. And then since 1996, he has been working on autonomous mobile robots, and he has been teaching that subject and anything related to that since 1996. He specializes in autonomous vehicle navigation, digital control graph, and motion planning and modeling of mechatronic systems. So that also includes a bit of digital signal processing and pattern recognition, which he also is in. And he also has an interest in engineering education. So he published a paper in 2001 on a competition-motivated capstone design course, result of a 15-year evolution, and it was published in IEEE class sections on education. So he's also interested in evolving the education scene so that it caters better to engineering students. He is also a Fulbright scholar. He was granted a scholarship to teach and research mobile robots and other applications. And he was involved with the Department of Electrical Engineering, University of I can't really pronounce that. So thank you, Dr. Master. So he accepted our invitation to be. He's also an acting faculty in School of Electronics, VIT Vellore. So he has been visiting VIT for the past few years, and he's here for a month. He has accepted our invitation to be here, and he'll be taking part of the building robotics course for you. As part of this, we have created a team, like I said. Some of you have already added. A few of you, your names I couldn't find. So if you're not there, please let me know at the end of the class and add you to the class. So over to answer.
Thank you very much for the kind introduction. So earlier when we were in the other class, I recognized the looks on your face as you saw us, talking in hushed tones and discussing the situation. Because I was in your position many years ago, and what we would hope for was that they would make an announcement that the class was cancelled. But of course, it did not happen today. But so I can read your minds. So the first thing I want to do is to reassure you that even though the title says autonomous mobility robotics, mobility is at the heart of all robotics. No matter what type of robotics you're doing, you have to have intelligent motion because that's how we operate. The only difference is that in the case of, for instance, robotic surgery, the base is fixed, whereas in mobile robotics, the base is moving. But having said that, they both have challenges that are common, and based on the application, one can be more difficult than the other. So it really depends on the application. That's what determines how difficult a particular challenge is for either one of these fields. Where you have a fixed base and you have a mobile base. Okay, so it's not my style to sort of go through every bullet. That's why I believe you have access to the PowerPoint and you can go through it and you can come and ask me. But basically this slide emphasizes the importance of terminology because when we talk to each other as engineers, it's important that we have the same understanding of certain terms. So fully autonomous really means that create a machine that is like a human being or animal. And such a machine does not exist and may not exist for the next 30-40 years. So it's a very loose term. So the driverless car would be like a fully autonomous vehicle in that particular category. But a driverless car cannot cook, right? So it's fully autonomous in that category, but even that has not been realized yet, and it will not be for the next 15-20 years. So what we have is semi-autonomous. That's what we manage with most of the time. And one example of that is ADAS, the advanced driver assistance systems. So most high-end cars already have ADAS, and now gradually those features are drifting down into lower-priced cars because it's getting cheaper to incorporate them into, in US dollar terms, $24,000 would be considered a low-end car. So you're getting features like lane keeping even in those type of cars. And then of course, automated parking is a very useful feature to have because most of us are not very good in travel parking, and that's also being incorporated. Now, the last category is like a compromise because there are situations where the machine can operate independently, but sometimes it needs human help. So you have this application in, I believe in the UK, where you have these huge trucks, we call them 18-wheelers. In the US, they have 18 wheels, literally, and they carry a lot of cargo. And the idea is that you can have hundreds of these trucks. Right now there is a safety driver, but eventually there won't be any driver. Most of the time they'll be able to operate on their own, but there'll be some people in the control room, centrally located, that will be watching what is going on. And so if a truck gets into a situation where it cannot navigate because it doesn't have that kind of intelligence, the human being will intervene and perhaps with the help of a joystick or something, it will get the truck through that particular situation and then put it back on its autonomous mode. So it seems more likely that we have the third category of applications come to fruition earlier than the others. So these are the two worlds of robotics. So medical robotics falls in the stationary robot category. Stationary in the sense that the base is stationary. Of course, the rest of it is not stationary. So we call them robot manipulators. And the picture here is the best example of what I mean. It's been around since, I would take a guess, from 1950s to 60s. We've been doing assembly line operations like welding and assembly and so on with those robots. And then we have the more futuristic humanoid robot. So that's a mobile robot. The only difference is that it doesn't roll, it walks. Because human beings like to see robots that look like them. So that's the only difference between a humanoid robot and a car that is a robot. So here's a quick comparison So it's not that one is easier or one is more difficult. As I said a few minutes ago, it depends on which application you're talking about. So there are many more degrees of freedom in a robot manipulator. Just because we try to create arms with multiple joints and they add up. There's something like 23 degrees of freedom in just one arm, in the human arm. So 23 degrees is kind of difficult to control. Mobile robots don't have that many degrees of freedom. A couple of wheels, and maybe the ability to turn. So it's always less than 10. More often less than 5. Whereas 23 in one arm, so look at those arms there and the joints, and you can imagine it's a much more difficult task. The second thing is the source of power is not an issue because the base is grounded, it's possible to plug in, and you're never going to run out of power unless the power fails. Mobile robots have this challenge, what kind of energy system you're going to incorporate so that you don't run out in the middle of a vital operation. The second thing is that the awareness of location becomes more important because the wheels are moving and wheels can skate. It's like counting steps, right? If somebody blindfolds you and says, take 100 steps and we repeat that operation 10 times, we'll end up in a different spot each time. So that's the same uncertainty that you have with a moving vehicle. Now, of course, if you're driving a car, we look around and confirm where we are. That is essential for us to figure out, where a moving platform is. For the manipulators, if you know the angle of the joints, you can typically figure out where we call this the end effector, like the tip of the fingers. You can figure out where it is provided we know the angle of the various joints. And then, of course, if you're going to go for a futuristic humanoid, the humanoid is the one with legs, then balance becomes a major problem. We learn how to balance very early on in life, but teaching that to a machine is not easy. Okay. So, that last sentence should be qualified. So, mobile robots is generally a more difficult problem. Right? Generally, right? But not always. Because if you take an arm and put it on a mobile platform, now you get the problems of both areas all combining together. So where would a machine like that be used? So you know that we live in an era where there's a lot of terrorism, bombs being left somewhere and so on. And you don't want to send a human being to defuse it, right? Because of the danger. So that's why they put an arm on a moving platform. And now it's a really challenging task. Imagine that at the end of this, once the bomb is found, you have to use those fingers of the robot to defuse it. That's a very difficult task. Even a human being is a difficult task. But if you're going to do it with the help of a robot, it becomes almost impossible at this time. So these are the different sub-areas of robotics. It's one of the most interdisciplinary areas in the world. So there are people who specialize in one of these areas, and there are people who are more systems engineers. They have a broad understanding and they bring systems together. So it really depends on what you want to do. So you can go through it on your own. I'm not going to read through it. And of course, software is like a thread that stitches everything together these days. So software is going to be present. So there's a home for an electrical engineer, a computer scientist, and a mechanical engineer. So these are the three branches that typically deal in robotics. So now I'm going to go through the sub-areas of robotics. So the first one is motion control, because if you're going to move, then obviously you've got to move with some plan in mind. Just like when we go from one classroom to the other, we don't just wander around. We walk with purpose, we have a map in our head, and we walk towards the elevator. So to make a machine do that is not easy, right? We do it regularly. So, but even before that, we have to have some means of moving. So the Mars rover, this is not the latest one, this is one of the earlier ones. You can see how complicated it is in terms of the mechanism. So you have to figure out electric motors, how many are you going to use, how many wheels. See that the reason that it has a total of 6 wheels is because it's a rocky terrain, right? It's not like Earth where you can control, you can create roads and so on. So you have to have certain degrees of freedom so that the front wheel can by itself, elevate and come down and so on. So the architecture is important. And then once you have the architecture, you have to figure out what are its capabilities in terms of motion, and then you have to be able to control it. Now, when we start doing some software exercises, you'll find that the way we command a robot to move is with two commands. Essentially, it's forward speed and then rotation rate. So those, you don't need to remember it right now, but it's V and omega. V is the forward speed and omega is the rotation rate. So many degrees per second. So essentially, that's how you command a robot in a simulator as well as in the real world. So no matter how many motors you have, somehow you have to relate the capabilities of the motor to these two basic commands. So the human being is not concerned about whether you have 3 motors or 4 motors. You're going to tell the robot to go V omega, and you're going to keep on changing the V omega. You realize that even an athlete, they constantly change their forward speed and the direction in which they are moving. So in the same way, the robot will be told V and omega constantly because the path is changing. You can't just give it V omega and say, okay, I'll come back after an hour. So you're constantly changing the path, just like when you're walking or running. So the second area is sensing and perception. So robots need sensors, and these are some of the common sensors used in robotics. The first one is the LiDAR. And when we start doing simulation exercises, you will learn how to access LiDAR data and then process it. And based on what you see, you can issue a V and omega command. So literally you're going to say, where are the obstacles around me? So just like we have eyes, the robot will have a LiDAR. And it's going to see objects around it, and then you're going to decide where you want to go. And based on that, you're going to issue a V and omega command. So if there's a gap on the right, it will be a certain V and omega. On the other hand, if there's a gap on this side of the robot, it's going to be a different V and omega. So you have to process the scene using the LiDAR returns and then give it a command. And then of course there's always signal processing involved. We have science known as digital signal processing, because when you read data from sensors, you will have noise on top of the sensors. It's inevitable, right? No signal comes clean. There's always noise on top of it. So you might have to remove the noise. You might have to do a Fourier transform operation, averaging. All those are lumped in the domain of signal processing. Now, one thing that is very important to point out is what is the difference between sensing and perception. So sensing means just the raw data, right? A camera gives you an image, so that's sensing. But I can see where the different students are in this class, right? If I just take a camera image, that won't tell me anything. So obviously there's some post-processing that goes on in order to make some sense out of the scene, right? That's how we move and drive, because we're able to deconstruct the scene in front of us. It becomes more difficult if it's night or raining, right? So still, to a certain extent, human beings still manage to figure out what's going on around them. So the camera image is the sensor data. The perception is what you really need, right? And as we grow up, perception is learned by experience. We know what the difference is between a dog and a cat, a pencil, an iPhone, and so on. So that's what we're trying to get machines to also realize. Now, in the case of a moving robot, the most important thing is, can it identify the lane lines? If the lane lines are drawn. Of course, in Chennai, it doesn't matter whether there are lane lines or not, because people are all over the place. But if you can identify the lane lines, can you then get the car to stay within the lane lines? So you also see some cameras. The one on the top right is a stereo vision camera. It is basically, because we have 2 eyes, right? And the reason we need the second eye is because that's the only way you can perceive depth. So the camera on the right, it's a product called Bumblebee, and it enables you to see like a human being can. You do the perception. You have to do the perception. So this is perception. You see the vision system has figured out where the lanes are. So essentially those are the colored lines drawn on the left. And on the right, you're using a 3D LiDAR. So a 3D LiDAR gives you an intensity pattern of the scene around you. And from the intensity pattern, it's possible to figure out the road surface. See, the blue part is the road surface because the intensity is kind of uniform, smoother. So obviously, human being can face smoother, but you have to make the computer understand what smoother is, right? So it's not that easy. But the blue is the road surface, and you can see on the side it's rougher. That's not the road surface, so you don't want to drive there unless you have a tank. So perception gives you that ability to figure it out. So robotics also involves localization, and typically that localization and mapping come together. Localization means people will immediately say mapping. So localization and mapping, because the two are done together. So what is localization? So localization is knowledge of where you are. And of course, in its most absolute sense, what does localization mean? You want to know where you are on the planet Earth, right? But sometimes that's not important. You want to know where you are within the classroom. And then may want to know where you are within the campus. And then you may want to know where you are within the state. So there are different levels of hierarchy, right? We typically are not interested in where we are on the earth that much, because the task requires knowledge of where we are in our locality. So, if you have a map, it's not useful at all unless you know where it is. You know what I mean? So I grew up in an era where we used to drive with maps open on our knees. We'd be saying, okay, look for a right turn, in about a mile. Now that's no longer needed because your phones do it for you. But essentially, when you tell a computer, you'll see once we get into the heart of the course, the computer still needs to localize the way we used to in the old days. So for instance, if you're looking for a particular restaurant, right, and it's approximately a mile, so you'll be walking and you'll have a rough sense of how much progress you're making, right, because it's a mile away, so you need to start looking for that restaurant when you're closer, right? So there is a rough distance calculator, which is your steps, and then you're going to look around and you're going to look for, Sarvana Bhavan or whatever it is you're looking for, right? And the problem is there could be multiple Sarvana Bhavans, right? So you have this combination of counting steps, and I call it looking up, because you're looking at your surroundings. Steps alone are not enough. As I told you, if you do 100 steps, 100 times you end up in a slightly different place, right? So you're confirming the step count by looking for a certain result with your eyes, right? That's exactly how we localize. So unless you know your location on a map, the map is useless. The reverse is also true. That, if you know where you are and you've been told to go somewhere and you don't have a map, then you're still, lost. So the two go together. You have to know where you are, you also have to know, where you are on the map. Only then you can execute a mission. So as I say there, the typical way in which moving robots, record or figure out where they are is by counting the wheel rotations. You'll see shortly, this whole course is accelerated. So typically, I would say to my students in a few weeks, but this is going to happen next week, you will see how odometry works. And exactly how by counting the rotations of the wheels, we can roughly figure out where we are. Now, why do I say roughly? Because counting the rotation of the wheels is like counting your own steps. Because what if you have two drive wheels and one wheel was slightly overinflated? You can imagine that, like one wheel is slightly overinflated. So, if the overinflated wheel goes one rotation compared to the normally inflated wheel, it is turning more, right? So, you're actually, if you're just counting on those two wheels as a drive mechanism, you will be turning to the left. So, normally if you run the two wheels at the same speed, you'll be going straight. It's not going to happen when you overinflate one wheel. So, that's why odometry is not going to be perfect. It is going to be like a human being counting steps. So, you cannot rely on odometry for long. You need confirmation. How do you get confirmation? GPS. So periodically you have to get a GPS reading and then correct your position. It's correct in the sense that odometry is constantly, getting more and more inaccurate. So it's like the step count, right? You count 50, 51, 52, but now you're getting a little bit tired, so your steps are shorter, right? You're not making the same confident strides. So you need to look around. That's the GPS reading. That looking around is like your GPS reading. So that's the mechanism that's going to be used. You'll see how we combine these two together. Now, in medical robotics, let's use surgery as an example. Localization is supremely important. When you operate on a knee, it has to be at a specific spot. I happen to know this because my brother is a surgeon. You cannot be a little bit like you can't be an inch off, certainly, unless you want to be sued. So there has to be a rough way of moving the knife to the general area, right? But general area is not enough. So after that, there has to be some kind of GPS type of confirmation. You're going to look at the knee and say, okay, is this the right spot? And move the end effector with the knife. So the same operations are involved. It's not specific to mobile robots or fixed robots, right? Anytime you want to get something to a certain spot, then the same skills are involved. So there's a technique known as kernel filtering. We won't do particle filtering because it's a little bit too complicated for this class. But we're going to simplify and explain the technique of kernel filtering, and that is going to be used. Kernel filtering basically combines the step counting with the looking around. In other words, odometry with GPS. You can't just average the two. It has to be done statistically, and that's what kernel filtering is. So as I said, robotics, you can't do localization without mapping or the other way around. One needs the other. So mapping is explained quite well by this figure on the right. So typically the way a robot maps, let's say you're looking at a new house, you map exactly the same way. Now in these days, you get an electronic copy of the map. But let's say you just want to get a feel for the house. You enter the front door, you will look at the drawing room area, right? And then you see the door to the bedroom. So you are creating a mental map. You could actually have a piece of paper and sketch it out. So that's exactly what a robot is going to do, except that it doesn't have eyes. So you have to use sensors to do it. And on the right, you see a robot, trying to create a map. It has to move around. So if I look at a wall from this angle, and if I look at the same wall from this angle, there's a difference, right? So what's the difference between this and this? Isn't it localization? So unless I have good localization information, I'm going to put this view of the wall and this view of the wall in the same place. That would be wrong because I'm looking here versus looking here, right? So localization is a constant worry. If you start putting things on the map without worrying about which direction you're facing, and it's not just which direction you're facing, I could be here and looking at the wall, right? So if I don't adjust for this, the map will be completely screwed up. So the two go together. So the mapping has to go with precise localization and vice versa, right? So you can see the robot has found the walls. But there are other areas that, the gray areas, it has not explored. What it has not seen cannot be on the map. How could it? We don't know what we have not seen in the house, right? So how would the robot know? So it has managed to find most of the walls. How did it do that? Did it stand in one place? No. You have to drive the robot around, or it has to autonomously search the whole house. And what will happen when you search the whole house in a random manner? You will come back to the same place and see the same wall again. If you put the same wall in a different position on the map is going to look like, completely mixed up. So every time you see the same object, you have to recognize that and adjust. You have to say, okay, I'm looking at the same wall, right? Now, this is the technique known as SLAM. And so we're going to do a little SLAM exercise with a simulator and MATLAB. So you don't have to do anything for that because, it's a CAN program that illustrates how SLAM works. It's quite nice actually to see that. So as moves around, the robot often sees the same wall and puts it in a different place. But then it has a mechanism, it's a mathematical technique where it figures out that this can't be the correct location because this looks like what I saw earlier, and then it joins the two together and eventually the map comes together. You'll see that. So last slide here in the first part. So what is the topmost ability of a human being? It's the brain, right? So every intelligent machine, whether it's stationary or moving, you're trying to give it a brain, and that is obviously the most difficult task. So you can have a separate class on the techniques that make up cognition, and you don't even have to mention robotics, because cognition is just like making something brainy, right? You don't have to have any reference to robotics. You can have multiple classes. So when you hear all these buzzwords like neural networks, right? Artificial intelligence, fuzzy logic, right? Evolutionary programming, they're all different methods to what? Make something intelligent. They are mathematical models of trying to incorporate in a machine what humans have routinely. So the thing is, a machine needs that kind of guidance, right? Maybe we have neurons in our head, but we don't really care, We grow up, we learn. But when you want to teach a machine to do that, there has to be some structure. And that's why you have all these many, many disciplines. Neural networks, fuzzy logic, evolutionary programming, artificial intelligence. And these are all separate courses on their own. So this is the biggest area of robotics. So eventually whether something becomes autonomous or fails, depends on how well you do this part. Now, the area we focus on, I told you, here's an example of cognition, Get a machine to defuse a chemical bomb. Now, of course, that's a legitimate area of cognition. But that is so specific, right? It'd be boring to a class like this, or even to me, because, great, but what am I going to do with that, right? It's very specialized knowledge, useful knowledge, but it's kind of a limited part of the entire spectrum of applications. So typically what we pick as an example of cognition is path planning, because no matter what type of robot you have, it has to plan a path, because the assumption is that the task requires moving from point A to point B, right? We all do that every day, we do it repeatedly. So that's typically the area that we focus on when we talk about cognition. We don't do everything possible in cognition, because we will be here forever. So here's an example of path planning. It's from a research study that we did for an army unit back in the States. So we have an algorithm known as D-star light, and they wanted us to evaluate the algorithm. So this, what you see here, these two rectangular boxes with seemingly fences in the middle, they represent a part of the building, an open area of the building where even in winter we can test. By the way, it feels great to be here, because I was telling Professor Abraham, the temperature a week before I left in Detroit was something like 2 degrees Fahrenheit maximum. 2 degrees Fahrenheit maximum, and that lasted for about 7 or 8 days continuously. So you can imagine. So even inside the house with the heat on, you will feel it in your bones. So in the center, the reason I brought that up was we have a central part of the building where we can't go outside and test a robot in the Detroit winter. It's just not possible. The battery charge will not hold for very long. It's very unpleasant. You have to have gloves. When you have gloves, you can't type on the keyboard. Then you have to take it off, and how long can you keep it off, right? So we have a central part of the building that kind of looks like this. So we created a simulation, model of that, and we also run the robot in the actual area. So basically, there are two snapshots of a robot, right, moving. This was before ROS, by the way. Before ROS, there was a thing called player stage, and the people who work on player stage moved to ROS and created ROS, and now they moved and created ROS too. So this is based on player stage. The upper one shows motion from a starting point to a destination. So you see the robot track when you're developing a map as you go. So you don't have a map initially, and somebody told you, "Hey, just go there, it's 50 meters away." So what will you do? You go directly towards that spot. And then the LiDAR picks up the fact that there is a fence, right? And then once it spots the fence, it says, obviously I can't go through the fence, so it starts to go along the fence, right? So there's a path planning operation going on in the background. And while it's doing that, it's looking at the fence and building a map of it, right? And then it finds the hole. So what does it do when it finds the gap? It says, okay, let me now go to that spot that you identified with coordinates, right? So it starts to go there, then it sees the second fence, right? And then it goes along the fence. And then it finds the gap again. So the zigzag path is because it's developing a map as it is moving. Whereas the second one, we told it, here is the map. And so if it has a map and it's smart, it says, why am I going towards the fence? Because I know I have to go along the fence anyway. So it goes just like a human being, right? He will not go along the fence if you have a map. So it goes directly to the gap. It's a shorter distance, and it finds the goal, much quicker. So what we were evaluating was how quickly that algorithm runs, the D-Starlight algorithm. When you get to the path planning module, we'll come back to this D-Starlight algorithm. So essentially, they wanted to know how long, because every time it sees a blockage, right? So by the way, it has no map. What do you think the map is in its head? Completely empty, right? That's the assumption you start with. Everything is empty. And then as it goes, it sees a fence piece, it puts it on the map. So the moment it sees the fence piece in its way, it has to replan, right? It thought it can just go straight and reach the goal. So it's constantly replanning. Do you realize that? It's constantly replanning in the upper challenge. Because it sees a fence and it has to say, okay, how do I still get to that spot? Because my old plan does not work. So that's called replanning. So they wanted us to evaluate how quickly this algorithm replans. Because you know what the problem is? Like human beings think seemingly instantaneously, but machines, you have to go through cycles, process cycles, and load this part of the memory, do some calculations, right? So what do you think happens if it can't come up with a quick result for the new path? You have to slow down. So if its brain is not functioning very fast, it will have to slow down, right? So obviously that's going to hurt your mission. If the army is running a robot in a battlefield situation, you don't want the robot to stop while it's planning, because then it could be destroyed. So they wanted us to know how quickly this algorithm will run in real time. And that's what we're doing. The last thing I want to mention, because before the first part ends, is that you are always mapping even if you're given a map. Do you know why? Because no map is complete. Because A, people make mistakes. So Google makes a lot of mistakes. Okay, I take it back. Not a lot of mistakes. They make some mistakes once in a while. So sometimes they tell you to turn, and you turn and there is a, the road is completely blocked, there's a permanent wall there. And because, they basically acquire maps by running cars all over the place. Did you know that? They actually pay people to drive cars, around. And they still haven't solved, Chennai. Because my brother's house, you can't get directions to it by going on Google. For some reason, it lists it in a different locality. So, obviously, there's going to be mistakes. And therefore, what we call the local map, right? The local map is what the robot sees, is constantly going to be compared to the map that you're given. And if there's any discrepancy, the local map will overwrite the global map. Because obviously, what the robot sees right now is the most important thing. It's the hottest piece of information, right? So you have to constantly change any map you're given. Second thing is, you may have moving objects, like a dog, right? That will never be on the map, right? How can Google map all the, cows and dogs, on the street? So basically, you are responsible for adding those to the map or removing them. Yeah? Maybe your house has been demolished, so it's no longer there. Alright, so that's the end of the first part. Second part. So these two PowerPoints should be available to you if they are not now. And you can go through them in detail. The second part has a number of links to videos. And I can't play all of them because we'll be here for many hours. So I'm going to sample some of those and you can watch the rest of it on your own. The other thing I wanted to mention is there's going to be 2 assessment exercises, like was mentioned earlier. And the way it's going to work is, so I'm going to grab your hand and sort of walk you into the forest, through the forest. So I'll give you some code and say, look, here's how it's working. And then you will be asked to add to it and finish it up. It's like I take your hand, we enter the forest, and then I say, okay, see, there is the opening, to leave the forest and go home. And so you will do that last part on your own. So and then I'm available to consult with. So it should not be that difficult. So we'll set you up with all the code and everything, so that all you have to do is finish it. Okay, let's begin with a question. So, the blood vessels in the body, right? If you add them all up in length, how long do you think they are? Take a wild guess. The total length of the blood vessels. So I didn't know this an hour ago. It's kind of relevant to the second part of the talk, so I googled it. How much? Anybody? What? Okay, nobody wants to answer. So this is what I found. It seems like too large, so it needs to be double checked. It seems like a reliable source. British Heart Foundation. So 60,000 miles of blood vessels are managed. Now, why this is relevant, we'll find out soon. So you can't believe that there'll be 60,000 miles of space, right? But apparently that's what it is, because it's so small and it's crisscrossing the whole body. So we'll find out why I asked the question shortly. So this is the second part. And let's get started with it. So this is the first application. This is more relevant to medical robotics, but I use it in my regular class. So this is the concept. As you can see, the reference is now 8 years old, so I'm sure they've made a lot of progress on it. So the idea is that they're creating tiny robots that they can float in the human blood vessel pathways. Now, why do you think they want to do that? Just to get information about you? Maybe, these days you never know. But here's the thing. So you have this, when you give somebody drugs, right? I'm talking about medical, not the other kind. There's typically a male dosage, there's 3 actually. There's no male female dosage. There is an adult versus a pediatric dosage, right? But it's a guess, because humans come in different sizes. Men are different from women. So really, we shouldn't be getting the same dosage, because you know that any medicine has side effects. Any medicine. There is no medicine without side effects. Even Tylenol has side effects. So we take the standard dosage, and so we can ask the question, should we really tailor the dosage to a particular person and a particular problem? Because when you sprain your ankle, it doesn't hurt the same every single time. Sometimes you have a mild sprain, sometimes you have a severe sprain, right? So why are we getting the same dosage? So the idea is that these robots will carry drugs, the appropriate amount. So that's the other thing. When you swallow it, a lot of it gets washed out before it gets to the destination. Because that's just the nature, right? When you swallow it, it gets digested into the bloodstream, and by the time it gets to the spot, it's maybe a couple of hours later. So the question is, if we directly deliver something where it's needed, maybe we can deliver less of it. So that is the idea here, that these nanorobots can be guided to specific parts, and that's why I brought up this the length of the blood vessels in the body. Because imagine now that your path planning and localization and mapping, all of those are needed here. You need to have a map of where you're going in order that the nanorobot gets there, and you need to have a path planned also. So a similar application. The first one is the traditional, well, it's not traditional because it's not that common, it's only experimental now, medical robotics, but getting robots to do surgery. And the main inspiration behind this is that by the natural order of things in life, we have very few expert surgeons. That's how it is. We have very few great cricketers, right? Because that's how it is in life. You can't have like a thousand Sachin Tendulkars. It just won't happen. So if you want to share these gifted doctors so that they can do surgery in many different places, you can't have them travel. They have to be able to do it from a central location. So that's the idea. You can imagine how critical and dangerous it can be, because if the doctor, the one doctor, makes a cut, and the patient thousands of miles away is cut in a different place, right? You can imagine. So you need some local people. First of all, you don't want that to happen. But if there is some side effects, you want local doctors to jump in and control the situation, because the main guy is not going to be able to do it from many thousand miles away. There's also, just like the nanorobots, there's an area known as endoscopy, and specifically magnetic endoscopy. You can see there is a capsule inserted in the intestines. So the intestines are not as long, definitely not 60,000 miles, because then we would be in trouble if we had 60,000 miles of intestines. But you move this, it's magnetic, and if it's magnetic, you can move it externally. And so you have to have an idea of localization, path planning and mapping, because you want to move it to the right spot. Now this one I'm not going to watch it though. It's fascinating to watch this. So I have some of these videos here. I can play it directly because I downloaded it, but the link is here for you. So you can cut and paste the link and you'll find it. So I want you to watch this on your own. Some we'll watch together. So this is not a video, it's just a concept. So one of the areas that robotics leans on is biomimicry. So biomimicry is our acknowledgement that nature has created some tremendous examples of intelligence, right? Not just humans, but also animals. So here, because you know that dinosaurs and humans never lived side by side, because one happened tens of thousands of years before the first human was seen. So they, by assembling the bones and so on, they try to figure out, humans try to figure out characteristics of dinosaurs, right? And in this particular case, they think this long-tailed dinosaur is using its tail for balance. When it jumps off, like let's say it jumps off from here to here, probably the distance is larger than that, but so a body can flip, right? Based on the center of gravity and the distribution of weight, and you don't want to land on your head. So these dinosaurs, they figured out, always landed on their feet, and they were using their tail as like a weight balancing system. So I think this is Stanford also, I'm not sure, but it's a paper in IEEE Spectrum. They designed the robotic vehicle with the same tail-like structure, and they're actually manipulating that weight so that the robot never flips over when it goes off a cliff. So a very useful property to have, right, for a vehicle, because you don't want the vehicle to tumble. This one we watched. I believe it's not working, because if it was not successful, she would not be able to move it. So essentially, she's just thinking about moving right foot, left foot, and the computer takes over and moves the right foot and left foot. That's not easy, because think about it. When we are walking, taking a walk, we don't think about moving at all, right? It just happens. So we are many years away from perfecting this, because to focus like that and think, okay, I want to put my left foot forward, it's not feasible to get people to think that heavily. There's got to be a simplified form of it, but of course you can't get there until you do something like this, right? You can't make it easy until you first figure out what is needed. So you may have heard that Elon Musk's company, he's got many, Neuralink, they just implanted a chip in a human being. So that's what they're trying right now. This is not implanted, it's external, which is less invasive, because who wants a chip in the head unless you know the complete effects of that. So this is a much simpler application along the same lines. You saw from the clips, the early clips, that precise localization is needed. If the patient is not so badly injured that they can move their head, it helps. But if a person is completely paralyzed, then localize, otherwise you're going to deliver the food, along the side of the face or on the forehead. So it helps if the patient can move a little bit, but if the patient cannot move, then the machine has to adapt. You can't blame the patient. So localization becomes very critical if the patient cannot even move a little bit, right? So it's all based on the application. That's my point. How accurate localization needs to be. Okay. You can watch that on your own. So these are two traditional, applications. This is a humanoid robot, the best in the world right now. So Boston Dynamics is a company that is based in Boston, obviously. But you can see it's a walking robot. This kind of balancing on ice, on snow, is very, very difficult. It's difficult for human beings, but it seems to be okay. See, it's doing what human beings would do, we would kind of stumble a little bit, but we'll recover. So it's got a very good control system. Almost went down there. So now you have arms as well as a mobile platform. See, the fingers don't have to be very sophisticated. That's why it's picking up a box. It's not doing surgery, so it can manage with just a flat plate. That's a real robot. There's no human being inside. So it's using the QR code to locate the sites. It would have been funny if it had turned around and attacked him.
Yeah. I was ready.
So, what's missing from these robots? They're kind of nice to watch, but the big question is, can they do something useful? Because otherwise you cannot profit from it. It's nice to watch, but then after a while people will get used to it and they won't watch anymore. So, finger dexterity, right? Very important in surgery. Because if you don't have finger dexterity, you can't do very sophisticated things. Even diffusing a bomb, you can't do it if you don't have any wrist, no fingers at all. If your arm is terminated at the wrist, you will not be able to defuse a bomb. So that's one thing. The second thing is human to robot interaction. Because we want robots to be like us, communicate with us like we communicate with each other. So if code is the only way you're going to communicate, it's going to be more difficult to get them to do what you want. You want to be able to talk to them, and that's improving. That's coming along. Siri and Alexa, they are so much more advanced than they were at the very beginning. But watch this. The reason I include this video is that the black flip is just amazing to me. We're going to backflip off the table now. I mean, most of us can't do that. Well, I don't know, maybe Professor Abraham. So this is the quadruped. Quadrupeds, bipeds. Bipeds are like human beings. Quadrupeds have 4 feet. So we're going to skip this. We definitely want to see this. Okay. Oh, I advanced it. This is a little bit slow developing, but you'll see it's quite amazing. So these are little robots of the kind you see in any robotics lab in a university, and they have little tiny grippers, and that's a real child. You can see the eyes moving, 2 seconds. And we've obviously designed the pants so that there are grips. A regular victim is not going to be lying in these pants, so that's going to be a challenge. So there are teams of robots, and the color indicates, so once the yellow grips the red, it will change color, I believe. So they form like teams of equal number of robots. So there will be a color change now, I expect. Yes, there it is. You can see the child is real, it's not a doll. There seems to be an imbalance, right? Because we don't have the same number of robots in each sub-team. There's one blue missing. Maybe they had a defective robot or something. That's pretty good. That's a nice demonstration, right? So, I think that's pretty much the aim. So, where do we need this? So, you may have noticed that because of climate change, there are increasing weather events, right? Even in Chennai. I grew up in Chennai, but my brother was describing the rain in late December. Was it like so much rain that you normally don't get at that time of year? So much flooding. So increasingly, you'll have situations where people will have to be rescued, and if you send other human beings to rescue them, you'll put those human beings in danger. Think of an earthquake, fire. In California, there's fire every summer. It's a given. You have to assume that it's going to be there. So these kind of robots are going to help rescue people because you don't put another human life at risk. So this is actually a growing area of robotics. So this is a more recent version of the same application. See, he's cooperating by moving his head. I don't know. I don't know whether people will take a haircut. For me, it doesn't matter. A person with hair is not going to feel comfortable having a haircut by a robot. So you can see what's going on here. So essentially you have a fake hand outfitted with sensors and actuators, right? And it's copying what the human hand is doing. So several years ago, there was this earthquake in Japan, after the earthquake or tsunami. Like earthquake caused the tsunami, and then you had that massive flooding and the nuclear power plant had to be shut down. Remember that? So essentially they had a situation where even after the shutdown there's radioactivity and they had to do other things. And of course you can't send a human being there. So this is the concept that would have addressed that situation if not just a hand, but you need a robot outfitted with things, tools of various kinds. So the idea is that a human being would be in a mock-up of the actual area where you want the robot to go. And the human being would show the robot what needs to be done, like turn off a valve, right? What is the big deal? Because remember the very first slide, fully autonomous? We're not going to get fully autonomous anytime soon. Maybe not for the next 30, 40 years. So one step closer to realizing a useful product is showing it, right? You have a human being in a safe environment showing it what to do, and it just blindly copies. For that you have to have virtual reality, because the person showing it is in a different place, right? The reality is somewhere else. So the person has to have a mock-up of the actual, hopefully it doesn't get it into the wrong areas, like, the military, because you can have human beings now fighting wars with robots, and because it's robots you feel that you can go totally crazy, right? And we don't want that either, like completely, knock out buildings and so on. So same idea, that this is an IEEE Spectrum article. You are probably familiar with IEEE, and Spectrum is their flagship magazine, and they have very nice articles. This is a few years old, 2019. So here's a guy outfitted with everything needed so that he can be sensed. As he makes, because there are multiple joints, right? You want to sense what each joint is doing, and then you want the robot to do exactly the same thing. So you have to have a mock-up. Maybe the axe doesn't have to be as heavy. In fact, I don't even see an axe. It's just got the grip. And if you want to break down a door in a nuclear power station, the robot will do it, but the human being will be showing how to do it. So this is an article. Do we have enough time to play this, or what can I? Yeah. Yeah, I may have it locally. Yeah. Oh, it's just an article. Or maybe there's a video. Let's see. So that's the micro robot next to a coin, so you can see its size. And here's the video. So you get the idea, right? So this is somewhat big to go into the body, but the idea is that they'll make them smaller. And so where does the vibrations come in? Because anytime you build a robot, you have this issue of where it's going to get its energy from. How is it going to move, right? And vibrations is a cheap way of making it move. Provided you can coordinate the vibrations. If it's just going to be random, then no use. So you have to be able to use the vibrations to push it. In other words, path plan and move somewhere. So that's the idea. You're trying to coordinate the vibrations so that based on the legs, you can actually make it go in different directions. So very interesting idea. So this is another concept that, in the US they have this law called the American Disabilities Act, ADA. And that means that every building has to be outfitted so that handicapped people can have access. Not just buildings, every park. So for instance, if you go to the Grand Canyon, you all know what the Grand Canyon is, right? So on top they have a 3-mile walkway. Anybody can drive up there and go up and down the south rim of the Grand Canyon. Just by themselves. No need for family members or others to own them. It's required by law. No steps. But what if you have older buildings? It's very costly to outfit older buildings with this kind of access, right? So then you need the machine to be able to overcome that. Because in Europe you have a lot more older buildings than the US. And part of the beauty of the buildings is the way they look. And you don't want to destroy that by adding access. So here is an invention. It's not playing. Maybe they pulled the video. Yeah. But you get the idea, right? So this wheelchair, normally you would be terrified that it's going to accelerate and kill the person, but it climbs the steps with wheels. So there's a braking arrangement. It cannot fail, and it goes backwards. If you could play the video, I don't know why it's not playing, but if you play the video, you'll see that it goes backwards, one step at a time. And that's the idea behind it. Here's another one. It is going backwards because this person is accompanying that person. And this was the suit, the young lady with the brain plugs, So this is the same thing now. This guy apparently is at a marathon or 7 kilometers, the Zurich marathon. This guy. So otherwise, he would not have been able to do that without the help of this. So it looks like it allows you to walk normally. Now this guy is not totally disabled. He's got some abilities and he needs a little bit of help. So that's what this picture shows. And all the links are available to you. So if you want to be inspired, I often say that the math is fine, but if you don't see the big picture as to why you're doing that particular course or a particular piece of theory, then it's useless. It will go in and out. So there has to be some kind of thread that holds it all together, some inspiration, and these applications are what give you the inspiration. I just want to mention this because it's not so relevant. So in the US, you have these 18-wheelers that are self-driving, and they go from coast to coast. Right now, they're confined to the warmer parts of the country because 2-degree Fahrenheit temperature, the roads get really bad, and I don't think any autonomous in quotes because there's no such thing can really deal with that. So the idea is, right now they have safety drivers because the law does not allow those to function on their own. The difference is that in California, they have created certain smaller sections of the city where they are running completely autonomous without any safety driver vehicles. So Google is doing that. They have a self-driving unit that you can actually get a taxi ride from these autonomous cars, taxis. The problem is humans are not patient. So they go very slowly because these cars will never be able to drive in Chennai with the way people cut across and everything. So they are meant to be cautious because they're meant to be safe. So So human beings will put up with it now because it's a novelty, right? It's fun, to be going without a driver. It's kind of fun. You can talk to your friends about it, but soon that novelty will wear off, and unless it gets you, like, how many of us have never been late, flying or getting to a class, never happens. Inevitably, every week you get a situation where you have to drive a little bit faster, run, walk faster. So eventually this model will not work because caution is how they avoid accidents, and that's not going to fly in America. It never will in the long term. So they have to get around that. So for instance, the same idea has been tried out in Arizona, in Phoenix. And what is the toughest operation for an autonomous car? So in US we drive on the right side of the road, right? So the left turn without a signal light. So meaning that you have to wait for the traffic to clear and then you take a left turn, right? It has not been mastered yet. It's a very difficult operation. So even Tesla, Tesla is supposed to be what they call a level 3 vehicle. Level 5 is full autonomy. I mean, Elon Musk will boast a lot. Some people say it's really a level 2, but he's made it a level 3 because he says it is. So how does it take a left turn? Not the Tesla, but this test vehicle in Phoenix. How would you take a left turn if you were too scared to attempt it? You take a right turn, and a right turn, and a right turn, right? 3 right turns to now go directly across the road. That doesn't work for most human beings. They're not willing to add 5 minutes or 10 minutes to their trip. So that's what the vehicle does. It takes a lot of, it abandons the left turn and takes 3 right turns to get there. So right now it's okay because people are amused, they're willing to give it a chance. But that's not going to work. The second thing is when it sees puddles of water on the ground, it often causes the LiDAR, the reflections and so on, causes a problem for the cameras on the robot. And the LiDAR is affected by billboards and so on. So that's the problem we're having. So these trucks are being tested out. The difference between trucks and regular cars is regular cars, right? A lot of the driving is done in the cities, which is the most difficult environment to be autonomous. But these trucks go cross country. Most of the time they're out in the highways. So they believe that they can make this model work. And the most difficult part, which when they approach the warehouse in a city, what they're going to do is the human being will get in. Right after that last highway ramp, you'll have a human being, taking over and drive it to the warehouse. And on the way out, the human being will drive it to the highway and then, get off, and then it will go on its own. So right now, they're actually running this. One of my students works in TuSimple, the first company listed. It went bankrupt, by the way. So I should really say he used to work for it. Now he's got another job. So essentially, it goes cross country. They're being monitored. There's a safety driver and slow speed. Stay on the right lane. Don't speed. Don't try to change lanes too much. It seems to work. I just want to run you through this. This is something that you should see on your own. This is a document that I came across. It's quite nice actually because it lists too many permissions. So here is a list. So it's a nice article to read because it takes you through the sub areas of medical robotics, surgical robots. We already talked about that. Robotics for radiotherapy, rehab. We saw a lot of rehabilitation robots, right? Helping people who are disabled. Laboratory robots, robot prosthetics, we saw that too. That lady in the beginning, she was wearing something and trying to use her brain. Hospital robots and social robots. So this is a good website to get an idea of that. And lastly, we will just look at the second link and we'll close it out. And that's this one. I believe it's a separate slide also. it's using that to, I guess they use that as a fill-in for surgery. It's they're pretending. So it's scratching out, a pattern on some kind of a rubbery substance. So just to show the idea, it's learning from the human what is the appropriate force to use. So that's the last slide, I believe. So if you have any questions, I can answer them. You know that I have an office, and next week onwards, you might have occasion to ask me once the first assessment exercise is assigned. Maybe the traffic will start then, and people will want questions answered. But that's fine. I'm looking forward to answering your questions. As I said, the homework, you're going to be led partially along, and then you're going to have to complete the rest of it.